All right, guys. Welcome to Unit 3, working with Windows and CLI systems. And you're probably wondering, CLI sounds very fancy. It's a command line interface. If you're curious, command prompt. That is CLI. So really basic systems. So let's go over the objectives of this chapter. We're going to explain the purpose and structure of file systems. This stuff will get a little dry, right? And I'm going to warn you. Describe Microsoft file structures. So you're going to learn how Microsoft works with their file structures. Explain the structure of NTFS disks, which are pretty common. List some options for decrypting drives, encrypting the whole disk encryption. So we're going to go over that. Explain how the Windows registry works. Should be pretty popular because you kind of run into it every day if you work on Windows machines. And you can kind of figure out how a registry works by seeing here are some examples. Describe Microsoft startup tasks. So what launches when Microsoft starts or Windows starts up, and explain the purpose of a virtual machine. So we're going to talk about VMs for a bit, which I can go on for days about VMs. I won't, so I'll make it brief. So let's talk about file systems right now. So let's understanding file systems. So what's a file system? So it gives an OS, an operating system, a roadmap to data on a disk. So it tells it, hey, hey, operating system, let's say Windows 10, for the sake of argument. I stored pictures in the picture folder. So it's going to know when you look for pictures to look in the picture folder. Types of file systems an OS uses determines how data is stored on the disk. Okay. When you need to access a suspect's computer to acquire or inspect data, you should be familiar with both computers' operating systems and file systems. So give me 1 second. Moving on to understanding the boot sector. Sequence, sorry. Sector is a hard drive reference. So, a temporary metal oxide semiconductor, or CMOS. If you look at a motherboard, there's a little watch battery on there. That's called the CMOS battery. And that stores a computer system configuration with the date, time, and information. It's really basic. It's for the basic input-output system, or BIOS. So, if sometimes, or extensible framework interface, EFI. That's a little over here. But in the same vein as a BIOS. If you don't know what a BIOS is, when you boot your machine, you press escape to get in the setup menu. That's the basic input-output system where you can edit settings like where it boots from, security settings also to lock it out or require a password to start up. That's all in there. So let's talk about understanding the boot sequence a little more. So the bootstrap process contained in ROM tells your computer how to proceed. Displays the keys you press to open the CMOS setup screen, which is the BIOS screen, not CMOS screen. I'll show it in the next page. CMOS should be modified to boot from a forensic floppy disk or drive. It should say BIOS. It's not phrased right, but let me show you. So this is what a basic input-output system is. BIOS. System name timers, everything's listed in there. So it detects the WDC, that's a Western Digital drive. HFS, that might be, I want to say Toshiba, but anyway, in there you would tab over to the boot section. And then there you tell it, hey, load from here. You can tell it to point to USB, boot to network, and that's where you would pick where you launch your software from. So if it's on a CD, for example, you would boot from the CD drive, which actually, sorry, that's what Ubuntu is. I apologize. That's the CD drive, not a DVD drive or hard drive. That is the CD drive. So you swap them and tell it to boot to there and load from the disk. So disk drives are made up of one or more platters coated with magnetic material, old spinning disk drives, which we cover next. Disk drive components comprise geometry, head, tracks, cylinders, and sectors. That's why you hear me say sectors sometimes. Ta-da! This is what they look like. There's about, I think, 7 platters. This is what these are normally called discs. We call them platters now, or been calling them platters for years. These normally have about anywhere from 7 to 12 discs or platters. Those are platters. Each circle is a track, right? So each line, it's an old record. Each have lines. Each wedge-shaped area is what's called a sector. So a whole area that makes up that sector, something is stored in that sector, if that makes sense. Each combination of tracks forms a cylinder, which is stacked on another platter. So if they're like this, in this section, that's a cylinder. It's up and down. That's the read-write head. That arm, it used to be pretty common. There's multiple platters. That arm is what enables it to be read, obviously, and write to it. Write down, is there a sort of picture, cylinder 4, whatever sector, blah, 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 blah. Something that you probably haven't heard the term back in the day, something called the head crash, where that would skip. It would be just like a needle, and it would just skip, and they wouldn't read, and then you're stuck. What do? You can't. You gotta take it to what's called a platter machine. That's why I say platter. Where you take it apart and put all the disks at the same time, and they read everything, and then you back up your data that way. But that's starting to get phased out because SSDs have taken over the world practically. So here's a disk platter. See, that's a platter. There's a track. There's 63 sectors making up that one area or area. 32 read-write heads. So look at that, all that. 124 cylinders, so 124 layers. 124 cylinders at 32 heads at 63 sectors is 2,064,384 sectors of data to read. 512 bytes per sector, which comes out to over a terabyte. Yeah, 1.056 gigabytes. Oh, sorry. That's barely a gigabyte. That's pretty fascinating, but this is something we don't really use that often anymore. So moving on. Properties handled at this drivers, hardware or firmware level, zone bit recording, track density, aerial density, head and cylinder skew. Don't worry, we're not going to have that on Zoom. Solid state storage devices. This is more what we use every day. Well, now, right? They're becoming industry standard more and more and more. All flash memory devices have a feature called wear level, an internal firmware feature used in solid state drives that ensures even wear of all read writes for all memory cells. When dealing with solid state devices, make a full forensic copy as soon as possible. It's crucial in case you need to recover data from unallocated disk space, because these write so much they burn out faster. Unfortunately, that's how you get those crazy ludicrous speeds of these things. But the problem with that is they wear evenly across. It's like you're filing away at something until you reach a point where it can't file that area, it jumps it and goes somewhere else. But it will warn you before that happens, before it boots, it tells you. But I don't have a picture of that. So exploring Microsoft file structures. In Microsoft file structures, sectors are grouped to form clusters. So now you're taking sectors and making clusters, like a cluster of stars. Storage allocation units of one or more sectors. Clusters range from 512 bytes up to 32,000 bytes each. Combining sectors minimizes the overhead of writing or reading files to a disk. Makes sense. Clusters are numbered sequentially starting from 0 in NTFS and 2 in FAT. It's a, what was it? I forget what the stand for. It's been a while, guys. FAT's a different kind of architecture. First sectors of all disks contain a system area, the boot record, and the file structure database. OS assigns these cluster numbers called logical addresses. It's getting confusing, I'm sorry. Sector numbers are called physical addresses. But it's Microsoft speak, I can't tell you what to tell you. Clusters and their addresses are specific to logical disk drives, which is a disk partition. So a partition is a logical drive. So that's when you sector out a piece of a hard drive and it becomes a partition or a piece. Part 2. Windows operating systems can have 3 primary partitions followed by an extended partition that can contain 1 or more logical drives. Hidden partitions or voids, large unseen gaps between partitions on disk. Partition gap, unused space between partitions. So you can sector out a hard drive however you want. So you can use like 20 gigs of a terabyte for, I don't know, pictures, music. That could be this partition. You can label it D when you activate it. The partition table is the master boot record located at sector 0 of the disk drive. In hexadecimal address, such as WinHex, you can find the first partition offset 0x1BE. The file system hexadecimal goes often 3 bytes from 0x1BE for the first partition. Here's what it looks like. It's kind of hard to read. I do apologize. So they have the first sector converted to decimal. 0 times 800 is 2048. The next one, bigger and bigger, and they just keep getting bigger. There's a partition file size. It's really hard to read this stuff, guys. I'm squinting myself. There's the offsets there. Numbers of sectors in each partition converted to decimal. It tells you what each sector is made of. Then first sector for each partition, and then just the size there as well. FAT. Here's what FAT means. File allocation table. There's 7 sides for this, guys. So file structure database that Microsoft originally designed for floppy disks. So it's pretty old. This has been around since the late 70s. FAT database is typically read to a disk's outermost track and contains file names, directory names, date and timestamps, the starting cluster number, and file attributes. 3 current FAT types: FAT16, FAT32, and EXFAT, used for mobile personal storage devices like portable drives. Well, anymore though, things going into TFS. So cluster sizes vary according to the hard disk size of file system. Here's a table of sectors and bytes per cluster. So anywhere from 8 to 32 megabytes, it's 1 sector per cluster, and FAT16 is 512 bytes. 32 to 64 megabytes, 2 sectors at 1 kilobyte in FAT16. 64 to 128 megabytes. Man, oh man, it's kind of redundant because it's not really seen that much anymore. 4 sectors per cluster at 2 kilobytes. It's kind of half is the way you could look at it when it comes to chirps for FAT16. Like if it's 2, it's only 1. The only difference would be the first one. But anyways, 128 to 256 megabytes. It's 8 sectors per cluster or 4 kilobytes. FAT16. 256 to 512. 16 kilobytes per sector. 16 sectors per cluster at 8 kilobytes of FAT16. 512 to a gig. 32 sectors per cluster at 16 kilobytes. 1 gig, 2 gigs, 64 sectors per cluster at 32 kilobytes on FAT16. 2 gigs to 4 gigs, 128 sectors per cluster at 64 kilobytes on FAT16. So moving on. Microsoft operating systems allocate disk space for the files by clusters, results in drives slack. Unused sectors in the cluster between the end of an active file's content and the end of the cluster. Drive slacks include RAM slack and file slack. An unintentional side effect of FAT16 allows large clusters was that it reduced fragmentation as cluster size increased. So here's what sectors look like. So a RAM slack is 128 bytes in the middle. The end of the 10 sector is 512 bytes of airspace. And file slack is 276 bytes here towards the end of it. End of frame, that's what EOF means. So it's 32 bytes. That's what 32 gigs of airspace there. So exactly if that discontinued 507. We're almost there, guys. We have about 50 plus slides to go. So we'll get there. But I'll give you a break. I'm about slide 34, give or take. Then we'll go from there. And I'll stop the lecture, and then it'll be a second. So we now have room for an allocated cluster. OSs allocate another cluster for your file. So we just slide it over. As files grow and require more disk space, assigned clusters are chained together, so it links things. The chains can be broken or fragmented. That's when crashes kind of tend to happen. Or get corrupted. Like you ever had pixeling, just got really weird after a while, like you're missing part of it. That's why. When the OS stores data in a file system, it assigns the starting cluster position to the file. Data for the file is written to the first sector of the first assigned cluster. Example of Word document clusters. See, it starts at cluster 479. That would be the beginning. Then it's written in cluster 479, 80, 81, 82, and 83 for a total of looks like 2 bits and 1 fragment. I wonder which one's a fragment. Chain sectors are located with clusters as a result of increasing file size. So I guess that became a 2 gig file. That's pretty weird. Or a Word document. It's a really big document. When this first assigned cluster is filled and runs out of room, that assigns the next available cluster to the file. If the next available cluster isn't continuous to the current cluster, a file becomes fragmented, so it gets all over the place. Deleting FAT files. In Microsoft operating systems, when a file is deleted, directory entry is marked as deleted file. When the hex E5 character replacing the first letter of the file name, FAT chain for the file is set to 0. Data in the file remains on the disk drive. Remember, you can't really delete data permanently. Area of the disk where the deleted file becomes unallocated disk space, able to receive new data from newly created files or both files needing more space. NT file systems. That's what NTFS stands for. Excuse me 1 second. Where's my mouse? Pause it. All right, guys. New type file system. Introduced Windows NT. Primarily file system for Windows 10. So improvements over FAT file systems. Remember, I told you FAT's kind of going away. NTFS provides more information about a file. NTFS gives more control over files and folders. NTFS was Microsoft's move towards a journaling file system. It records a transaction before the system carries it out. So essentially it logs what it's doing. And NTFS, everything written to the disk is considered a file. On an NTFS disk, first data set is the partition boot sector, so where it's loading Windows from. Next is master file table, so that comes after the boot sector. NTFS results in much less file slack space, so it's a lot more cleaner. Clusters are smaller for smaller disk drives. NTFS also uses Unicode, an international data format. So here's the table sizes. Cluster sizes at NTFS disk. Excuse me. I just had dinner. That's about 7:30, so I'm kind of processing it. We're from 7 to half a gig is 8 sectors per cluster at 4 kilobytes in cluster size. So the size doesn't really change until about 32 terabytes, which is kind of nice. From half a gig to a gig of data, it's still 8 sectors per cluster at 4 kilobytes. So that didn't change. 1 to 2 gigabytes, same thing. 8 sectors per cluster, 4 kilobytes. 2 gigs to 2 terabytes, it's still 8 sectors per cluster, which is pretty efficient. and 4 clusters kilobytes per size. Followed by 2 to 16 terabytes, same thing, 8 to 4. Here's where it changes. At 16 to 32 terabytes, it becomes 16, sections per cluster, at 8 kilobytes. So it doubled. At 32 to 64, it doubles again. 32 sections per cluster at 16 kilobytes. 64 to 128 terabytes is 64 sections per cluster to 32 kilobytes, and 128 terabytes to 256 terabytes is 128 to 64 kilobytes. So, did I skip a page? Hold on, guys. No, we're good. Sorry, just thanks for just be text. So NTFS files, system files. MFT contains information about all files on the disk, including the system files the OS uses. The MFT, the first 15 records are reserved for system files. Records in the MFT are called metadata. Things we capture. Here's what it looks like. File name is MFT, system file MFT, record position 0. Basic file record for each folder of the NTFS volume. Other record positions in the MFT are allowed if more space is needed. So it can kind of slot some things. MFT mirror MFT2, record position 1. So after the main MFT. The first 4 records of the MFT are saved in this position. If a single sector fails in the first MFT, the records can be restored, allowing recovery of MFT. So, log file. System file name, log file. It's pretty straightforward, huh? They all have the same practical. Record position 2, so it's third slot. Previous transactions are stored here to allow recovery after a system failure in the NTFS volume. So if it fails, you can go look at the log and see where it failed and see if you recover it from MFT2. Volume. System file name, volume, position 3, which is position 4 in reality. It goes 0 is 1, 1 is 2, 2 is 3, 3 is 4. Position 3, record position 3. Information specific to the volume, such as label and version, is stored here. There's more. So it goes up to a bunch of other items here. Sorry, I got the text, guys. Anyway, okay. Attribute definitions. This is position 4. The table listing attribute names, numbers, and definitions. Root file name index. Position 5. File name with $sign, so it doesn't have one. This is the root folder on the NTFS volume. That's the base folder. That's what root means. Bitmap is boot sector, which is what stores current map, MFT partition showing which clusters are in use and which are available. Boot, regular boot, position sector 7, uses to mount NTFS volumes during the bootstrap process. Additional code is listed here, and if it's boot drive for the system. So that's where essentially Windows loads from position 7, which is technically position 8. So we're going 0, right? So this is from 0 to 16. That's what's called, technically what's called circular array. But that's something you learn programming. Then we have bad cluster, which is bad cluster file, section 8. For clusters that have unrecoverable errors, an entry of the cluster location is made in this file, so it keeps track of what isn't loading in the clusters. Security file, record position 9. Unique security descriptions of the volume are listed in this file. It's where the access control list, ACL, is maintained for all files and folders on the NTFS volume. Cool. Uppercase table, position 10. Converts all lowercase characters to the uppercase Unicode character for the NTFS volume, and extended NTFS extended file, position 11. Optional extensions are listed here, such as quotas, object identifiers, and read parse pointer. That's all hard drive stuff. Then 12 to 15 are reserved for future use. So in the NTFS or my MFT, these are MFT and file attributes. All files and folders are stored in separate records of 124 bytes each. I know, guys, this is dry. Each record contains a file or folder information. That's not the best grammar in the world. This information is divided into record fields containing metadata. A record field is referred to as an attribute ID. File or folder information is typically stored in 1 or 2 ways in an MFT record, residence and non-residence. Files larger than 512 bytes, so files larger than half a gig, are stored outside the MFT. MFT record provides cluster addresses where the file is stored on the drive's partition, referring to as data runs. Each MFT record starts with a header identifying it as a resident or non-resident attribute. So here's what that looks like. A bunch of different attributes. They go from 10, 20, 30, 40, 50, 60, 70, 90, I'm sorry, 80, 90, and A0, because it can't use 100. So attribute 10, I'm just going to refer to them as 10, not 0x, whatever. Standard information, this file contains data on the file creation, alterations, MFT changes, read dates and DOS file permissions. 2 is reflective of the attribute list. Attributes that don't fit within MFT, non-resident attributes are listed here along with their locations. 30, file names. Long and short names for the file are contained here. Up to 255 Unicode bytes are available for long file names. I'm not going to go into it. It's a lot more. Don't worry, guys. It's not going to cover that much of the test, I think. Still have to write it, so don't worry. I'm not going to torture you. 40, object ID, volume_version in Windows NT. Ownership and who has access rights to the file or folders are listed here. Every MFT record is assigned a unique GUI ID. Depending on your NTFS setup, some file records might not contain this attribute ID. 50, a security inspector contains the access controllers for ACLs for the files. 60, volume name, the volume unique file identifier is listed here. Log file is the unique identifier. 70, volume information, the file indicates the version and state of the volume. 80, data, file data for resident files or data runs for non-resident files. 90, index root, implementation for users of folders and indexes. And A0, index allocation, implemented for use of folders and indexes. So, and this keeps going on. We got B0, bitmap. A bitmap indicates cluster status, such as which clusters are in use and which are available. Reparse point, which is C0. This field is used for volume point amount points and installable file systems. What the hell? Sorry. Filter drivers for the highest and mark specific files used by drivers. So when you load a driver, it loads there. G0, EA information, which uses OS-2 HPF. Don't worry about that. E0, same thing. And 100, which they actually used. Logged utility stream. This file is used for encrypting file systems, EFS, and Windows 2000 or later. Something you run into. And here's what that looks like. Hold this go. Give me 1 second, guys. Okay, guys, this is where we left off. I took a little break because my sanity, and this is slide 35. So I'm going to talk about this real quick. Well, we just mentioned prior. And then after that, we can stop the lecture here. It'll be part 1 of this lecture. Then I'll make the second part. So as I was mentioning earlier, so here it says B0. I know it's really hard to see all this for A. So here's the things we talked about. Remember, go 0, 1 through 9, then A, B, C, D, E, then 100 will be out here. So A, here's that there. All MFT records start with file 0. So that would be here. I know it's weird. It's this. See, that's what it's referring to. Start of attributes 0, attributes 10 I talked about, so that's here. Then what's followed by that? Length of attribute is 60, so let's see. So it tells me how long it is there. I know it's really confusing, guys. I'm just going to really go over this. I'm not going to quiz you on this, don't worry. Length of, and then it starts for 30. I guess 20 isn't available in this one. Here's its length, 40. Attribute 40 I talked about. Here's a length value of 28. That's value 70. So this guy's the biggest so far. Where are we now? I did F. Yep, that's that one. Then I'm gonna start of attribute 80 here. Length of 70. So that's the same as E, which is where is 30 here, same length. Then starting position for resident data is K here. It's hard to read this stuff, guys. I know it's really small, but don't worry. I don't think there'll be that much about this stuff in the exam. So I will see you in the next one, okay?